Alternating series stuffs. The alternating series does summation from n equals to 0 to infinity of minus 1 raised to power n of an with an greater than 0 converges if the following two conditions hold. First condition, the nth term must be greater than the nth plus 1 term. Second condition, the limit as n tends to infinity of the nth term must be 0. An alternative series is of this form. Now, when the sequence is strictly decreasing and the limit of that sequence is tending to 0, then that alternative series is said to converge. Let's take some examples. Example 1. Discuss the convergence of the alternative series. Now the series is of this form: 1 minus 1 over 2 plus 1 over 3 minus 1 over 4 plus. So this is a question, and we have to prove that this alternative series converge. But how do we know it is an alternative series? An alternative series, the sign of each term changes from positive to negative to positive to negative. Like the first term 1 is positive, second term negative, third term positive, fourth term negative, hence it is alternating. Now, this particular series can be rewritten as the summation of what we have here, that the summation from n is equals to 1 to infinity of minus 1 all raised to power n all over n. If we expand this, we're going to get this series back. Now, remember that from the definition we have something similar. Let me write it out, which is the summation from n equals to 1 to infinity of minus 1 all raised to power n of an. Now, if we compare these two expressions, we see that an should be 1 over n. Why? Because this is the same thing as the summation from n equals to 1 to infinity of minus 1 all raised to power n times 1 over n. So hence an is 1 over n. So an is equals to 1 over n. Now, for this series to alternate, there are two conditions. The first condition is an should be greater than an plus 1. So we're going to find an, we'll find an plus 1. Remember that an is equals to 1 over n. We're going to check if an is greater than an plus 1. An is equals to 1 over 1 when n is 1, 1 over 2 when n is 2, 1 over 3 when n is 3, 1 over 4 when n is 4, 1 over 5 when n is 5 to infinity. So an is equals to 1, 0 0.5, 0 0.33, 0 0.25, 0 0.2 to infinity. You will observe that the first term is bigger than the second term is bigger than the third term is bigger than the fourth term, and the fourth term is bigger than the fifth term. So therefore, we have that an is always greater than the next term, which is an plus 1. So the first condition is satisfied. Next, let's move to condition 2. The second condition for this alternative sequence to converge is that the limit as n tends to infinity of an should be equals to 0. Now, let's solve this limit. An is equals to 1 over n. Now, what's this limit? The limit as n tends to infinity of 1 over n is just like writing 1 over infinity. When we substitute n for infinity, and 1 over infinity when they will limit is 0. So, this is also true. Hence, both conditions are satisfied. an is greater than an plus 1, and the limit as n tends to infinity is 0. So when solving an alternative sequence, the first thing you need to find out your an. Take note that in your an, the negative sign will not appear. An is always positive. Then you check if the sequence is decreasing. The sequence must decrease. The first term must be greater than the second term, must be greater than the third term, must be greater than the fourth term. That is, an must be greater than an plus 1. Now if this condition is true, that is condition 1. Then we solve for the limit as n tends to infinity of that very sequence. And if the answer is 0, means condition 2 is satisfied. If both conditions are satisfied, then the series is said to converge. Example 2. Discuss the convergence of the alternative series. The series is of this form. The summation from n equals to 2 to infinity of minus 1 raised to the power n all over ln n. I want to prove that this series converges. The alternative sequence has the form, the limit for n equals to 1 to infinity of minus 1 all raised to the power n of an. Now when we compare both expressions, an is equals to 1 over ln n, because this expression here is the same as the summation from n is equals to 2 to infinity of minus 1 raised to the power n times 1 over ln n. So if we compare this expression here and this one, we'll observe that an is 1 over ln n. So the sequence is 1 over ln n. There are two conditions for the series to converge. First of all, this sequence must be decreasing, and also the limit must tend to 0. So let's work with decreasing. For it to decrease means that an must be greater than an plus 1. The sequence an is equals to 1 over ln 2 at n equals to 2, because we begin from 2. Then 1 over ln 3, 1 over ln 4, 1 over ln 5 to infinity. So an is equals to 1 over ln 2, 1 divide ln 2. The answer is 1.44, 1.44. So the second term is 1 over ln 3. 1 over ln 3 is 0.91, 0.91. The next term, 1 over ln 4. 1 over ln 4 is 0.72, 0.72. The next is 1 over ln 5 is 0.62, 0.62, and the list keep on going. So the question is this sequence increasing or is it decreasing? 1.44 is greater than 0.9, 0.91 is greater than 0.72, 0.72 is greater than 0.61. Hence, an is greater than the next term, which is an plus 1. So we have proved that an is greater than an plus 1, which is the first condition. Now for the second condition, the limit of an should be 0. So the limit as n tends to infinity of an should be equals to 0. Now let's check if this is true. Now the limit as n tends to infinity of an is 1 over ln n, is equals to 1 all over ln infinity. Of course, ln infinity should be infinity, and that gives us 0. When dealing with limit, 1 over infinity is 0. So the other condition is satisfied. So since the sequence is decreasing, that is an is greater than an plus 1, and the limit as n tends to infinity of the sequence an is 0, hence the series converge. If you want to learn more about the alternative series types or any other tests related to convergence tests, you can message me directly on WhatsApp. Meanwhile, subscribe to this channel, share and like this video. Bye.